Welcome back, AP Chemistry students, to Unit 2, Chemical Bonding. Today we'll be talking about covalent compounds. In the previous unit, we talked about the bonds between metals and how metallic bonds forms. We also talked about ionic compounds, which are salts formed when metals lose electrons to form cations. Those electrons are picked up by nonmetals, which form anions, and they form a crystalline lattice where the cation is surrounded by anions, the anions are surrounded by cations, and the pattern repeats forever and ever and ever. So when we write the formula, we don't say how many ions of each are present, we show the simplest ratio of one to another that balances out their oxidation state. So for table salt sodium chloride, sodium with a +1 charge and chloride with a -1 charge, it would be a 1-to-1 ratio. That was ionic compounds. Ionic compounds are held together by electrostatic forces, an attraction between something positive and something negative, and the force of that attraction is proportional to the charges divided by the distance. That was all Unit 2.1. There's a transfer of electrons that occurs. However, not everything is a metal and not everything is a salt, so let's talk about the other type of chemical bond that you need to know for this class: covalent compounds. Covalent means that electrons share valence electrons. This attraction is significantly weaker, but it occurs because the nucleus of an atom will attract electrons in neighboring atoms towards it. So if I have two atoms, that electron is equally attracted to both nuclei. This attraction holds those two atoms in close proximity to one another, which creates a covalent compound. They share a valence electrons, covalent. Typically, covalent compounds occur between non-metals. So remember nonmetals on your periodic table. Draw a diagonal line from boron to the corner because chemistry is boring. Nonmetals make up the right-hand side of the periodic table. So things like carbon, nitrogen, oxygen, chlorine, fluorine, these are the normal players in a covalent compound. So again, the big difference here: in ionic compounds, you form ions, which form a repeating pattern, a formula unit. However, covalent compounds, there's a sharing of electrons between the two nuclei, and this sharing holds those nuclei in close proximity to one another. Now, how well an atom shares its electrons is its electronegativity. Remember, electronegativity is greatest in the upper right-hand side of the periodic table and least in the lower left-hand side. That's because atoms in the upper right-hand side are the smallest, while atoms on the lower left-hand side are the biggest. And so an electron in a bond is significantly closer to the nucleus of a small atom and experiences a much stronger attraction than an electron involving a much bigger atom experiences a much weaker attraction. So when there's a massive difference in electronegativity, if one atom has a much higher electronegativity than the other, this difference in electronegativity causes the more electronegative atom to rip or strip an electron from the least electronegative atom. This is how ionic bonds are formed. The definition of an ionic bond is when the difference in electronegativity is greater than 1.7. If the difference in electronegativity is less than a half, then the two atoms share the electrons in their bond equally. The attraction between the electrons and the nuclei are the same, and so the electrons spend an equal amount of time around both nuclei. This is known as a covalent bond, specifically a non-polar covalent bond. There's a share of electrons, so no poles occur. But when there's a difference of electronegativity that's not massive but sizable, electrons will be more attracted to one nuclei than the other, and so they will spend more time around that nucleus than the other. Spending more time around that side causes that side to become partially negative. We symbolize partially with a lowercase delta. partially negative side has more electrons. It's the side with the greater electronegativity. So chlorine here has a partial negative charge. Hydrogen, with less electrons around it less often, becomes partially positive. This is a polar covalent bond because I have two poles, a positive end and a negative end. There's a dipole moment for this molecule. That moment is the electron spending more time around the more electronegative end. We often show dipole moments as arrows with a plus end where the positive where the partial positive charge is, and the arrow shows where the electrons are spending more time, the negative end. Now, electrons are shared or given so that elements reach their lowest energy level. The lowest energy level is to have a full s and p orbital. So a full s and p orbital for any element is to have 8 electrons in its outermost shell. Showing just the outermost shell of an atom is known as its Lewis dot diagram, where you show just the valence electrons, the s and p orbital. So for oxygen in column 16, it ends in 2s2, 2p4. 2 plus 4 is 6. Oxygen has 6 valence electrons. So we show these valence electrons as dots around the symbol for oxygen. Each dot represents an electron. So in practice, please try to space your dots around that symbol on its 4 sides equally. So for example, nitrogen in column 15, nitrogen ends in 2s2, 2p3. 2 plus 3 is 5, so nitrogen has 5 valence electrons. So its Lewis dot diagram would be 1, 2, 3, 4, and then you could double up and make 5 dots. So again, to reach their lowest energy state, elements will gain or lose or share electrons to have 8 electrons in their outermost shell. For fluorine here, it is short 1 electron from having that octet, so fluorine forms a covalent bond with itself, sharing another electron, giving each fluorine 8 electrons. This is known as the octet. Now, most of the time in this class, we're going to focus on molecular covalent compounds, which are molecules that float through space-time on their own. The formula is the actual number of each element needed to reach their lowest energy state, to share the correct number of electrons to have that octet. However, that is not every covalent compound. Some covalent compounds form when elements form large lattices. These are known as network covalent solids. Network covalent solids are things like diamonds. A carbon has 4 valence electrons. It's in column 14. So it could share an electron with 4 other carbons. By sharing with 4 other carbons, that carbon has 8 valence electrons reaching its lowest energy state. This is what happens when diamonds form. Carbon forms 4 covalent compounds with other carbons, which form 4 covalent compounds with other carbons, and the pattern repeats unto infinity. A network covalent solid would be something like a diamond or sand. Also is an example of a network covalent solid, or even the pencil lead that you write with. Graphite is carbon, which forms rings. Those rings stack upon one another, and when you run your pencil across the table, what you're really doing is releasing those rings onto the paper. But again, for the vast majority of this course, we are going to focus on molecular covalent solid, where an atom is sharing the number of electrons needed to reach that lowest energy state and give it 8 valence electrons. Now, when it comes to covalent compounds in this class, we are going to focus on simple covalent compounds where each formula tells you how many of each atom is present. So writing the name of these compounds is simply a matter of telling me how many of each element is present in that formula. We use the Latin prefixes mono, di, tri, tetra, penta, hepsa, hexa, octa, nona, and deca to tell you how many of each element is present. There is one exception to this. We never use mono with the first element. You can use mono for anything else, but never the first one, because it would be redundant. So for example, on page 14 on the top, you're asked for the formula names for each compound. For number 6, you have Si2Br6. Si is silicone, and Br is bromine. But since it had to have had a negative charge to come second in this formula, since it is the less electronegative atom, it becomes bromide. Now we say how many of each element is present using Latin prefixes. So 2 silicones would be disilicone, and 6 bromines would be hexabromide. S is sulfur, and chlorine, being the second formula, must have a negative oxidation state, so it becomes chloride. Since we have only one sulfur, you might be tempted to write monosulfur, and 4 chlorines would be tetrachloride. However, remember, mono never goes on the first element, so this is just sulfur tetrachloride. Going from the name to the formula is just as easy. It's just a matter of writing the symbol and telling me how many of each one you have. Antimony, the chemical symbol is Sb, and tribromide, bromide would be bromine. Tri means that there are 3 bromines. So we have SbBr3. Number 2 has a typo. Let's see if you can find it. That's right. In order to say silicide, we need to know how many there were, so the second element here should say monosilicide. Boron, its chemical symbol is B, and hexa means that there are 6 of them. Silicone's chemical symbol is Si, and mono means that there are 1 of them. Now, before you do page 14, one quick note here. Some chemicals have been around for millennia. We know their elemental symbols and names. You do not need to name them their IUPAC, or the International Union of Pure and Applied Chemistry nomenclature. What you need to do is just name them based off of what you know them to be. So anytime you see H2O, you know that's water. Don't call it dihydrogen monoxide. That's kind of pretentious. Same with ammonia. NH3 is ammonia. Methane is CH4. Methane belongs to a group of compounds known as organic compounds, where carbon is the backbone of them. We will talk about organic compounds in much greater detail at the end of the year, but for right now, CH4, just call it methane. With that being said, you are able to finish the top of page 14, pause the video, and do page 14, just the top. We often represent covalent compounds using what are known as Lewis structures, done by the work of Gilbert Lewis, who worked on a lot of acid-base theories. Gilbert Lewis was specifically looking at why something like boron trifluoride behaves as an acid when it doesn't contain any hydrogen ions to donate. We will talk more about his work when we get to acid-base chemistry, but before we do, you have to be able to draw what are known as Lewis dot diagrams, or Lewis structures. Lewis structures focus on valence electrons, the electrons on the outside, which are used in bonding. Again, a good trick to determine how many valence electrons something has is to look at the column number it is in. If something is in column 13, it has 3 valence electrons. Noble gases have 8 valence electrons, except for helium, which only has 2. Alkaline earth metals have 2. The number of valence electrons generally is the last number in the column. This is true for representative elements, those in the S and P block. The transition metals, it's a bit more of a complicated story, but this is a good rule of thumb. So with a periodic table in hand, let's talk about Lewis structures. In a Lewis structure, we show electrons as dots. So fluorine in column 17 has 7 valence electrons. We can show them around the 4 sides of the element fluorine. So electrons form pairs. It takes a pair of electrons to attract both nuclei into a bond. So electron pairs can either be owned by a single atom, such as here, this nitrogen owns this lone pair that it alone holds in this bond. Or they can be in a bond. Bonded pairs are electrons held between 2 nuclei. We will show electrons as dots or lines. A line represents 2 dots or 2 electrons. So if I want to draw the Lewis structure for carbon tetrafluoride, I need to know how many electrons are going to go into this compound, specifically the valence electrons. So I'll grab my periodic table. Carbon tetrafluoride, carbon here, and fluoride here. Carbon in column 14 will allow me to use 4 of its electrons, its 4 valence electrons, while each fluorine in column 17 will allow me to use 7 of its electrons. There are 4 fluorines, so if I add up how many electrons I have to work with, I have 4 plus 4 times 7, or 32 electrons in total. Now that means that in my picture I can have no more than 32 dots. But they always form pairs because it takes a pair of electrons to form a bond. It takes 4 pairs of electrons to reach the lowest energy state. So oftentimes I don't think in terms of how many electrons I have, I think in terms of pairs. So I always divide that number by 2 to say I can have 16 pairs of electrons in my formula. Now it's a Lewis structure, so one of these has to be our central atom, the one in the middle. The central atom is going to connect all the others. Our central atom is always the least electronegative element, as long as it is not hydrogen. Generally speaking, whichever element is first in the formula is going to be your central atom, because in order to be first in a formula, you have to be the least electronegative element present. So carbon's going to go in the center, and fluorines are going to go around it. Lewis structures are based off that 4 sides of that letter, so let's put the fluorines top, bottom, left, and right. You connect these outside or terminal atoms to the central atom with a pair each. So of my 16 pairs, I use 4 pairs to connect my terminal atoms to my central atom. So of my 16 pairs, I now only have 12 pairs left. We will now start giving everybody their octets, starting with the terminal atoms. So we're going to start with the fluorines. We are going to give them their 8 electrons to reach their lowest energy state. So starting with this top one, it already has 2 electrons around it. To reach its lowest energy state, it has to have 8, so I'll give it 3 more pairs. So of my 12, I have only 9 left. On the right side here, this fluorine has 2 already, so I'll give it another 3 pairs to give it the 4 it needs to reach its lowest energy state. I have 6 electrons left. On the bottom, this fluorine has 2. Here's 4. Here's 6, 8. I have 3 pairs left. This fluorine has 2, so 3 more pairs reaches its lowest energy state. I'm all out. If I had any left over, they would go on the central atom on carbon, but since I don't have any left over, I need to check to make sure I'm at my lowest energy state for everyone. So I go back and check. Carbon, 2, 4, 6, 8. Carbon has its lowest energy state. Each one of my fluorines has 8 electrons around it, so they're at their lowest energy state. As long as everyone's at their lowest energy state, this is a valid Lewis structure for carbon tetrafluoride. Let's try again. Find the example in your packet. Nitrogen trichloride. We'll need a periodic table and a calculator. For nitrogen trichloride, nitrogen in column 15 is going to allow us to use 5 of its electrons to work with. There are 3 chlorines. Each chlorine is going to allow us 7 of its electrons to work with because it's in column 17. For a grand total of 26 electrons or 13 pairs of electrons. So nitrogen is going to be our central atom with 3 chlorines around it. We're going to attach the nitrogen to our chlorines using a pair. We have 13 pairs, so we used up 3. We have 10 pairs of electrons left. Remember, a line is the same thing as a pair of electrons. So let me do all dots this time. We're going to give each terminal atom its octet, its 8 to reach the lowest energy state. So on the right side, this chlorine has 2, so here's 4, 6, 8 electrons around it, reaches the lowest energy state. Giving the chlorine on the right side its octet used up 3 of our pairs. We have 7 pairs left. On the bottom, we have 2 electrons already. So here's 4, 6, 8, using up another 3. We have 4 pairs of electrons left to work with. On the left-hand side, we already have 2. There's 4, 6, and 8. We have 1 pair left. Any pairs left go on the central atom. So for nitrogen, it's going to pick up that extra pair. Now before we say we're done, we need to double check. Does everyone have their lowest energy level? Does everyone have 8? This chlorine has 8. 2, 4, 6, 8. This chlorine has 8. This chlorine has 8, and nitrogen has 8 as well. Since everyone's at their lowest energy state, this is a valid Lewis structure for nitrogen trichloride. For the sulfate ion is sulfur with 4 oxygens around it that has a -2 charge. So again, to figure out how many electrons we have to work with, we'll need a periodic table. Sulfur in column 16 is going to allow us to work with 6 of its valence electrons. There are 4 oxygens, and each one will allow us to work with 6 of their valence electrons. Now, before you finish counting, there's something of note here. Sulfate is sulfur with 4 oxygens that collectively has a -2 charge. The only way you could get that -2 is if you had extra electrons. So if you have a ion, you need to add or take away electrons based on the charge. Negative, add electrons. Positive, take away electrons. So we're going to add 2 electrons to our total here. So 6 plus 4 times 6 would be 5 times 6, which is 30, plus 2 is 32 electrons that we have to work with, or 16 pairs. Sulfur goes in the middle, oxygen's around it on its 4 sides. Connecting the sulfur to the 4 oxygens is going to take up 4 of my pairs. I have 12 left. I'm going to give each terminal atom its octet. This time let's just do all lines. So use up 3 to give the top oxygen its octet. 2, 4, 6, 8 uses up another 3, giving the right side its octet. 4, 6, 8. We have 3 pairs left. 2, 4, 6, 8. We're all out. If we had any left, they go on the central atom, but we don't. So for sulfate, here is our Lewis structure. Sulfur and all of its oxygens have their octet. This is a valid Lewis structure for sulfate. In a little while, we're going to reevaluate this, but for right now, good enough for this example. Let's talk about carbon dioxide and cyanide. So find their next example. For carbon dioxide, we grab our periodic table. Carbon is going to give us 4 valence electrons. It's in column 14. There are 2 oxygens. Each oxygen is going to provide 6 electrons, for a total of 16 electrons or 8 pairs. We can draw no more than 8 lines or 8 pairs of electrons for this molecule. So carbon, our least electronegative atom, is going to go in the center. Oxygens are going to go on 2 of its sides, so let's just go left and right. We have 8 pairs of electrons we can work with, so we'll use 2 to connect the central atom to our terminal atoms, giving us 6 pairs left. Give the terminal atoms their octet, so each oxygen is going to use up 3 of our pairs, reaching their lowest energy level. We have no pairs left. Before you finish and say, yep, that's an answer, you need to double check. Yes, each oxygen is at its lowest energy state. Each oxygen has 8 electrons around it. However, carbon has only 4 electrons around it. This is not a valid Lewis structure. However, carbon's special. Carbon is one of a handful of elements that can share again. Remember when we talked about network covalence, like carbon has 4 valence electrons, and I said, oh, it could form a bond with 4 other carbons. Carbon, nitrogen, oxygen, phosphorus, and sulfur all are able to share more electrons. They can form other bonds. Now, carbon could form bonds with 4 individual carbons, or it could share again. Both oxygen and carbon are able to share again. So what we could do, rather than draw any more electrons, is to make this oxygen and carbon share a second pair. Instead of making 1 bond, making 2, or a double bond. So the elements carbon, nitrogen, oxygen, phosphorus, and sulfur are able to share more than once. In the interest of being fair, let's pull this other electrons from the other side. Making each of these oxygens share twice with carbon allows us to give each oxygen its 8, but now carbon also has 8 by forming 2 double bonds. Why don't you pause the video and try cyanide? Not literally, but why don't you draw the Lewis structure for cyanide? With 5 pairs of electrons, you might have reached this step and realized, yes, you're going to have to make nitrogen share again. but that's still going to have carbon be short. So nitrogen actually can share a third time. So you should end up with something that looks like this. So here is a valid Lewis structure for cyanide. One thing we haven't talked about yet is the fact that this is an ion. When you have ions, you put them in brackets with the charge in the upper right-hand corner so that you know that there are extra electrons present. So on our previous example of sulfate, the best answer would have been to put this in brackets and write a -2 to denote that this is an ion. Now, when we talked about valence electrons, I pointed out that, hey, helium only has 2 electrons. It only has 2 valence electrons. Well, that means that it violates this octet rule, where the lowest energy level is to have 8. There are actually a couple elements that violate this rule, right? Like hydrogen has 1 electron. If it gains 1 more, it would be isoelectronic to helium, so hydrogen's actual lowest energy level is to have 2 electrons, or 2 valence electrons. Another one that breaks this rule is boron. Boron's nucleus is too weak to support 8 valence electrons. So boron actually is satisfied with having 6 valence electrons. Or boron is at its lowest energy state when it has 6 valence electrons. So let's see this in action. Boron triiodide. Boron is our least electronegative atom, so it's going to go in the middle, and we put 3 iodines around it. Now, how many electrons do we have to work with? Boron in column 13 is going to provide us 3 electrons, and we have 3 iodines. In column 17, iodine is going to provide us 7 electrons to work with, for a total of 24 electrons, or 12 pairs. Connecting the central atom, the boron, to the 3 iodines uses up 3 of our pairs. We have only 9 left. Each iodine is going to require 3 pairs to reach its lowest energy state. So that uses up all 9 of our electrons. And while each iodine has 8 electrons around it, boron has only 6. However, boron is okay with that. Boron's at its lowest energy state by having 6 electrons around it. So this is a valid Lewis structure for boron triiodide. Some nuclei are too weak to support an octet. Some nuclei are strong enough to support more than an octet. After magnesium on the periodic table, the D sublevel forms. Elements larger than magnesium with a nuclear charge of 13 or greater have a D sublevel where they can put electrons. This is known as an expanded octet. Meaning silicon or selenium or chlorine could be at their lowest energy state with more than 8 electrons around them. So for our next example, selenium hexachloride, selenium in column 16 is going to provide us 6 electrons to work with and 6 chlorines. Each chlorine will provide us 7 electrons for a total of 48 electrons, or 24 pairs. Selenium is our least electronegative atom, so it goes in the center. Chlorines go around it. So we have left, right, top, and bottom. Well, why don't we put the other 2 just a little off the center? Connecting them costs us 6 pairs, so of our 24, we're down to 18. And each one is going to require 3 pairs to reach its lowest energy state. So of our 18, none are left over. And while each chlorine is at its lowest energy state with 8 electrons around it, selenium has 12 electrons around it, but that is okay because selenium with a nuclear charge of 34 is able to support an expanded octet. With that, you're able to do some more of page 14. Pause the video and draw Lewis structures for 11 through 14. Now, in your Lewis structures, like for example, for carbon dioxide, every connection between two atoms is known as a sigma bond. Sigma bonds fall within the plane of the nuclei. Pi bonds have to form above and below or to the left and right of the nuclei. Pi bonds are any bonds after the first, meaning in carbon dioxide, between carbon and each oxygen, there's a sigma and 1 pi. So in carbon dioxide, there are 2 pi's and 2 sigmas. When we did the Lewis structure for cyanide, the first connection we drew between the two was a sigma bond. However, any connection after that, this triple bond contains 2 pi bonds. Bond order is the number of bonds divided by the number of groups bound, or terminal atoms. So for example, in our carbon dioxide example, there are 4 bonds. 1, 2, 3, 4. And there are 2 terminal atoms. So our bond order for carbon dioxide is 2, meaning there's a double bond. This is a much stronger attraction than, say, carbon tetrafluoride, where there are 4 bonds and 4 terminal atoms, so a bond order of 1. The higher the bond order, the more dense that electron cloud is, meaning this attraction between nuclei is much stronger than this attraction. That pulls the nuclei closer together. So a triple bond would be the shortest distance between 2 nuclei, while a single bond would be the longest. This is also why there's no such thing as a quadruple bond. If you had 4 pairs of shared electrons, the attraction would be so much that the nuclei would overlap. So you cannot have a quadruple bond. Bond order can also reveal if there's not a clear double, single, or triple bond, such as the case for nitrite. If you draw the Lewis structure for nitrite, you end up with this. If you look at the bond order here, there are 1, 2, 3 bonds with just 2 groups bound. This is a bond order of 1.5. So what type of bond is it? Well, it's actually kind of both. It's a single bond and a double bond, but that double bond can flip-flop. You could just as easily draw this with the double bond occurring on the left side. These are what are known as resonance structures, where the double bond exists in both places. So anytime you come up with a fractional bond order, that means there's more than one possible Lewis structure. Resonance structures are separated by a double arrow to say that these options all exist simultaneously. Now, in order to determine which option is at its lowest energy state, we look at formal charges. Overall, the charge of a molecule has to be the sum of the formal charges. So if you were to add all these numbers up, +2 + 4 - 1s is a -2. Overall, formal charges will equal the charge of the compound. But a formal charge looks at an individual atom within a compound and examines the number of valence electrons minus the number of electrons owned by that atom. where each bond represents one electron owned by that atom, because the other would be owned by the other atom in that bond. So for example, this oxygen here in sulfate, oxygen in column 16 has 6 valence electrons, and there are 2, 4, 6, 7 electrons owned by that oxygen. The overall formal charge, the formal charge of oxygen in this example of sulfate is -1. Having charges means you have more energy, and the idea of forming bonds is to be at the lowest energy state possible. So a good Lewis structure minimizes the number of formal charges, and if anything does have a formal charge, the most electronegative atom has the highest negative formal charge. So in our original example of sulfate, every single atom had a formal charge. Each oxygen is a -1. Sulfur in column 16 has 6 valence electrons. It only owns 4. Each bond only counts as 1, so 1, 2, 3, 4. So sulfur's formal charge, the way we drew it, is a +2. That makes this Lewis structure, while valid and a resonance structure for other options, it is not the best option. It has too much energy. You can change formal charges by changing how electrons are shared. If you put in a double bond, look what happens to this oxygen. If I put in a double bond, oxygen in column 16 has 6 valence electrons, but by having it share, it now has 2, 4, 5, and 6 electrons. Its formal charge drops to 0. That's one less formal charge to look at. That's less energy to start with. And look what happens to sulfur. Sulfur in column 16 with 6 valence electrons now owns 1, 2, 3, 4, 5 electrons. So its formal charge is a +1. For sulfate, the best option with the least number of formal charges is option C. Here we have 3 atoms with no formal charge, and our most electronegative element, oxygen, has a formal charge on it. So that's why that is the best option for this. Example 6 has us look at xenon trioxide. Xenon comes after magnesium on the periodic table and can have an expanded octet. Overall, we have 26 electrons, or 13 pairs. Drawing it the way we've learned so far, xenon connected to 3 oxygens causes us 3 pairs. We have 10 left, giving each oxygen its lowest energy state, takes us down to 1 remaining. This is a valid Lewis structure. However, if we look at the formal charges, each oxygen in column 16, 6 valence electrons, each oxygen has 7 electrons around it, so each oxygen is a -1 for its formal charge. Xenon in column 18 has 8 valence electrons. Its formal charge, in the way we drew it here, is a +3. Overall, this is true. This is a valid Lewis structure. It is neutral, but every single species has a formal charge. This is not the best way to draw this. This has way too much energy. So we could change the way the electrons are shared. While xenon is not one of the exclusive elements that can form double bonds, by being able to have an expanded octet, xenon is able to form double or triple bonds. You probably will never have to reiterate that, but just so you know, I could have made one of these oxygens share. This is going to change the formal charge of 2 of the players here. Now, this oxygen in column 16 has 6 valence electrons. This one shows it with 6 valence electrons, so the formal charge of this oxygen is 0. Each of these oxygens is still a -1, but xenon is now also in a better place. Xenon has 2, 4, 6 electrons around it, so its formal charge is a +2. This is slightly better, but again, we could still show it with less energy. So you're smart, you're pretty, gosh darn it, people like you. You've probably figured out that every time I put a double bond, that's dropping some of these formal charges. Each one of these oxygens is now has a formal charge of 0. This oxygen is still a -1, but xenon is in even in better place here. The lowest energy resonance structure for xenon trioxide is for xenon to have 14 electrons around it, because each oxygen is now a formal charge of 0. And xenon 2, 4, 6, 8, xenon's formal charge is now 0. And so the best Lewis structure, the best resonance structure for xenon trioxide is actually this last one. So on page 14, there were 2 structures that came up with fractional bond orders. I believe they were nitrate, and ozone. Draw other Lewis structures and based on formula charge, circle which one is the most appropriate. With that, we are done with unit 2.2. Make sure you do your AP classroom homework. Next class, we will talk about the shape molecules take based on these electrons in their valence shell, known as valence shell electron repulsion model, or VSEPR.